from the about point to where the force is applied. Yeah. Linkages, yes. And
I concur.
So last time we started talking about linkages, and I'm going to finish this example. Yeah. And then after that, I'll give you a set of steps that you can use generally for these problems. But the example we were doing was this thing that doesn't look equilateral, but it's supposed to be. Each of these lengths was 1 meter. Each of the masses was 10 kilograms. And there was a 1,000 Newton force here. Can anyone confirm through your notes that this is what the problem was? Okay. Okay, so what we've done so far is from rigid body kinetics of each member. We got 4 equations. That was rotational Newton's second law for member, let's call this member 1, member 2. This is A, B, and C. Our 4 equations were rotational Newton's second law for body 1. And then for body 2, we had Newton's second law and rotational Newton's second law. And so this was 1 equation, 2 equations, 1 equation, and so that adds up to 4. And variables, oh, before I do that, why is there no Newton's second law for body 1? That's right, because it has a fixed point, so we didn't have to use it. Yep. So variables, well, we had the reaction force at A. We had the contact force between 1 and 2. We had the contact force at 3. So I'll call that RC. It's a scalar because we know the direction. Then we had the angular acceleration of body 1. Then we had the translational acceleration of body 2's center of mass. And then we had the angular acceleration of body 2. That comes out to be 9, I believe. 1, 2, 3, 4, 5, 6, 7, 8, 9. But since we didn't, so these are the variables, well, these are the acceleration variables plus the loads that come up in the free body diagram. But since we didn't use Newton's second law on body 1 because it has a fixed point, and RA acts at our about point, this one doesn't come up in Newton's laws. So this goes away and you get 7 variables. Okay, so this is that's a pattern that's going to be predictable. Like once I go through the steps, I'll try to point out why you always see this kind of stuff. So the question, already I asked why we didn't use Newton's second law for body 1, and it's because there's a fixed point. That's the same reason that we don't have an acceleration of the center of mass for body 1, because that would only come in, those translational accelerations only come in when you use Newton's second law. Okay, so 7 variables, 4 equations, and so we need 7 minus 4 equals 3 constraint equations. And those are going to come from yes, so the members can't fly apart at B. And there's no vertical acceleration component at C. Okay, so first let's do the one that says the members can't fly apart at B. So what's that is saying is if you calculate the acceleration of B according to member 1, that has to be equal to the acceleration of B calculated using member 2. All right, so let's first calculate the acceleration of B according to member 1. How are we going to do that? So just using the information from member 1, how do we calculate the acceleration of B? Yeah, watermelon equation. That's just circular motion around that fixed point. So this is just equal to alpha 1 cross the vector. I'll write this as the vector B minus A. You know, that's the R vector. Plus omega 1 cross quantity, omega 1 cross that same vector. I couldn't help myself. Oh yeah, I can imagine. Okay, and the centripetal acceleration term goes away because you don't have any angular velocity. And so this angular acceleration is in the z direction. So we got 0, 0, alpha 1 crossed with, we can figure out what that r vector is. It's 1 meter times cosine and sine of 60 degrees. So that's 0.5 0.866. And so you get negative 0.866 alpha 1 for the x component and positive 0.5 alpha 1 for the y component, and then 0. And we're only going to use the x and y components of this. It's a plain problem, so I'll just write it like this. Okay, so now how do we calculate the acceleration of B according to member 2? We have to use relative motion, right, because there's no fixed point. So we're going to assume that the center of mass is fixed and use the watermelon equation. So let me write this a little differently here. The acceleration of B relative to the ground is equal to, so this is for according to member 2, so acceleration of B according to the ground is equal to the acceleration of B according to the center of mass of 2 plus the acceleration of the center of mass of 2 relative to the ground. We could choose anything as this, as this sort of second frame of reference. Why did I choose the center of mass of body 2 as the frame of reference? Because that's where we know information. So that means that this acceleration of the center of mass of 2 relative to the ground is a variable we already, well, we don't know what it is, but it's already one of our variables, and that's what we want, is not to add new variables. So this one is the acceleration of the center of mass of 2. So that's good. And what's this one? How do we get that one? This is the watermelon equation. Okay, so if we're just going to add these two things together, we can think of, so the acceleration of B, according to member 2, is equal to alpha 2 crossed with the vector that goes to B from the center of mass of 2 plus omega 2 crossed with the quantity omega 2 cross B minus the center of mass of 2. And then we're just adding on the acceleration of the center of mass of 2. This goes away because I said when I gave the problem that it was at rest. And so this is equal to 0, 0, alpha 2 crossed with. So now we're going from the center of mass of 2 to that point B. So that's just from here to here. Okay. That distance is 0.5, so this is going to be 0.5 times, negative 0.5, 0.5 times positive 0.866.
And we're doing that because there's no fixed point on that.
That's right. That's right. So this is negative 0.25, positive 0.4330. And then we're adding on the acceleration of the center of mass of 2. Okay. The way I like to, so I've said this a million times before, but I think what you want is a system that is going to always work, and then you just want to keep doing the steps of the system, you know, and like the thinking about like what you expect, where you expect symmetry or this or that stuff is useful for sanity checking your answers after. But I'd recommend just getting in the habit of just like, I know I haven't given you this yet, but just keep plugging through, you know. So it just makes every problem the same, and it makes it less likely that you're going to make dumb mistakes as you go, you know. So you don't want to.
What's a smart mistake?
Yeah, it actually worked better. Like, wow, that went way higher than I thought it was going to go. That's great. Who does? Oh, Bob. Or happy accidents. Yeah, I like Bob Ross, but he and I are in sort of different businesses. Okay, so we got negative 0.433 alpha 2. No, that's positive. No, that was right. And then this is also negative 0.25 alpha 2. Plus a center of mass of 2. Okay, so this is equal to negative 0.433 alpha 2 plus a center of mass of 2 x component, and then negative 0.25 alpha 2 plus a COM 2 y component. And so now where we're heading with this is now we're going to set these two things equal. So we have, for our constraint, you know, let's think of it as the joint B constraint. We have negative 0.866 alpha 1, positive 0.5 alpha 1 is equal to negative 0.433 alpha 2 plus a center of mass of 2x, and then negative 0.25 alpha 2 plus a center of mass of 2 y component. And our constraint equations say, so this would be equation 5 star, says negative 0.866 alpha 1 plus 0.433 alpha 2 minus a center of mass of 2x is equal to 0. And equation 6 star says 0.5 alpha 1 plus 0.25 alpha 2 minus a center of mass of 2 y components is equal to 0. Any questions about that constraint equation for the joint at B? That's the pin joint. So what we just said is, as long as that constraint is enforced, that point has to stay, that point on the two members has to stay connected. That's what we said. And then the last thing we're going to enforce is a constraint equation that says this can slide in either direction, but it can't jump or sink. Okay, so we're going to say the y component of the acceleration at c has to be equal to 0. Okay, so the acceleration at c, y component is equal to 0. We're not putting any restrictions on the x component. That's what we're trying to calculate. Okay, so how do we calculate the acceleration at c? Well, we want the acceleration at c relative to the ground. That's equal to the acceleration at c relative to that same reference point, the center of mass of 2, plus the acceleration of the center of mass of 2 relative to the ground. And again, we chose that second reference point at the center of mass of 2 just because that's something we already have in our list of variables. You could do it for any point you want, but then you just add more variables, and that's, we're trying to catch up to the number of variables we have. Okay, so the acceleration at c, so this one is just the acceleration, the center of mass of 2. This one's the watermelon equation. So the acceleration at c is equal to, so alpha cross r plus omega cross quantity, omega cross r. What's the alpha we want to use? 2, that's right. So we got alpha 2 crossed with, what does our r vector go from and go to? Yeah, that's right. So c minus center of mass of 2, and then plus omega 2 dot 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 that goes away. Plus the acceleration of the center of mass of 2. So AC is equal to 0, 0, alpha 2 crossed with positive 5, negative, nope, this should be positive 0.5, negative 0.433, 0, plus a center of mass of 2. That cross product is positive 0.433 alpha 2, positive 0.25 alpha 2, plus a center of mass of 2 x and y components. We just want to say that the y component is equal to 0. And so equation 7 star, our last equation, says 0.25 alpha 2 plus acceleration of the center of mass of 2 y component is equal to 0. Okay, so now we have 7 equations, 7 variables. Make a matrix for it, solve it with reduced row echelon form. Yeah.
Is that why it's done on computers now? Because the arithmetic for doing this would just be
Yeah, and I think to me that's why, like computer calculations, good calculators and stuff are the reason that it makes sense to do these all as vector and matrix calculations now, and it didn't used to. Traditionally, people tended to think of it more as like scalar things, but now that you can do those calculations easily with a calculator, it's sort of more clear what you're doing this way, I think. Yeah. Yeah, I mean, I guess with calculators, we can do slightly more complicated problems in the same amount of time. I mean, in real applications, like in research and industry and stuff, then yeah, I mean, they're way more complicated than this, and so you have programs written, or you work on writing programs that then you can do these super you can imagine, like, conceptually it would be no harder to do a problem like this with 1,000 moving pieces and all these different joints. The approach is still the same, but no one would ever try to do that by hand. Yeah, and not just that, but the more equations you have, the more places are there for you to write the negative sign down wrong here or whatever, and it messes up your answers for everything, so. Yeah, but you have, so, yeah, 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 right, right. Any other questions about that? Oh, we're not going to solve that one because I don't have it here in front of me. But you are going to solve something like this. Not that bad, I mean, it's it it took a long time for us to go through this because I was trying to explain the steps as I went and whatever. And then how much longer does it take to type in a 7x8 matrix? Like not that much. So it's you've done harder things than this before. To do it correctly, yes. Okay. Okay, well, you better clear your schedule. So here are a set of general steps.
That way we have to take 4 years make sure.
They don't ask me about my opinions about how long an engineering degree takes, so I don't know. I think they should, but they don't, so. Yeah. That problem.
You also keep assigning that. So every time I come, we can't do this yet.
That's funny. Yeah. So if you remember, the thing with that one was that you had the axis of rotation of one of those bodies depended on the motion of the one it was riding on. And the way we're going to be able to do that is doing calculations in rotating coordinate systems. So we'll purposely choose a coordinate system that's rotating, and then we'll have to apply corrections to that so that the physics still applies. Okay, so first, okay, granted, number one is a big step. That's not listed on here. For each member, do a rigid body analysis. So in other words, step one of this approach is steps 1 through 7 of rigid body kinetics. So that means for each one of those, you're going to think about whether you have a fixed point or not, calculate the mass moment of inertia, free body diagram, Newton's laws, all that stuff. Okay. There are two possibilities here. If the member that you're working on has a fixed point, and the rotational equation gives you one useful equation. And the acceleration variable for that body is just alpha. If, when you get to bodies that don't have fixed points, so if the member has no fixed point, Newton's second law and rotational Newton's second law give three useful equations. And the acceleration variables that you get from Newton's laws are the acceleration of the center of mass, that's a vector, and alpha. Alpha, since these are all 2D problems, alpha is just the z component of the alpha vector. Step 2, at each joint that's not a fixed joint, I guess, that's not fixed ground.
Does it have to be affixed at the ground?
Yes, it has to be. So this has to be, so let's say that's only going to be pin joints in 2D. So, you know, in the problem we just did, there was the one pin joint connected to the ground. And if you think about the constraints we used, we never went back and calculated a constraint saying that that point A on the body is fixed to the ground. That's sort of done automatically in the way that we're treating it. But every other joint, we had to enforce what the joint does ourselves. So enforce the limitations point, puts on member accelerations. And this will always use two things. Watermelon equation and relative motion. And then once your equations catch up to your variables, solve using reduced row echelon form. Okay, so that's a good question. So on the exam, since this is the simplest version of a linkage you can have, you know, and that was a 7x8 equation, you know. Well, and this one would take, it wouldn't take as long as it took me to go through it, talking about it and stuff, but it would take the whole test, and I don't want to give a test that's just a single problem. So what I tend to do is like ask for pieces of these problems, like ask you to draw a free body diagram or list out the row and the force and the moment for specific, you know, selected bodies or something. Or I guess what I end up doing more is give me, just list out all the constraint equations. You don't have to solve anything, but you know, in this problem we needed 5 constraint equations, say, write out the 5 equations, and then I can ask other questions too, you know. But yeah, on a test, I pretty much never will have you go through a whole thing, because then the test doesn't get to have much on it, you know. Any other questions? So that's pretty short, 3 steps. That's great. Yeah. And I said this as we were doing the example. But these are some things that'll help. I think the people who took statics with me, this is how I always had you think about this stuff, so it'll be pretty natural. But for the people who didn't take it with me, I think this might help. Things. And this is mainly just for your free body diagrams. Once you've done your free body diagrams, you'll be sort of done thinking about this. So first of all, using this notation is really helpful. Like the force on A by B, FAB is force on A by B. Newton's third law says the force on A by B is negative force on B by A. And so you'll need to use that to reduce the number of forces down to the minimum you can have. Like in our example, we have body 1 and body 2. And body 1 up here had the force on 1 by 2. This one had the force on 2 by 1. But Newton's third law says we don't have to treat that as 4 separate variables. We can just treat it as 2 variables. Call this one, for this body, F12, and call the one over here negative F12. Okay. So this allows you to minimize the number of force variables. And then the last thing is you always, at pin joints, I guess this only applies at pin joints that connect members, so you wouldn't do this for the pin joint that connects the thing to the ground. Assume the pin is part of one member only. Okay, so for example, if you have a problem where there's one member, there's another one, there's another one, they're all connected by a pin. So I'll call this member 1, 2, and 3. And let's say that there's a force vector applied, F. Here's how we imagine this going. So here's somebody watching from the side. So what does this person see? This person sees member 2 over on the left side. Yeah, right. So that's what I'm trying to draw here is basically he's looking straight down member 2. And then member 1 goes off this way diagonally away from him. And member 3 goes away from him diagonally down. So this is 1, 2, 3. Dang it. Yeah. No. 2, 1. Okay. And just so that I always do it the same, I just always happen to decide that I'm going to call the pin part of the lowest numbered member. So, so to me, I'm going to assume that that pin is part of member 1 and the other things are connected to that pin. Okay. And then that force F is applied not to 2 or 3, it's applied to that pin. So when I do the free body diagram of member 1, it's going to have a force 1, 2, because this touches the pin. It's going to have a force 1, 3, because this touches the pin. And it's going to have a force F. Okay? But now think about when I do a free body diagram for member 2, what forces does it feel? Like 1 felt all these things, but 2 is only connected to the pin. It's not connected to 3, and it's not connected to, and that F isn't applied to it. So this one only has F21 or negative F12. And same with this. It doesn't feel member 2. It doesn't feel F. It just has the force on 3 by 1 or negative F13. Okay. Any questions about that? Okay. And I'll do another example next time.